Hello everyone, this is the Unit 1 pretest review. As always, I highly recommend that as you're going through and solving the problems that you take some time to self-reflect on the learning targets and the objectives, and kind of be your own judge on how well you are understanding the individual topics, and not just the problems that you're doing, but do you understand the topic? So, questions 1 and 2, finding limits. Most of the time, when evaluating a limit, it's as easy as plugging in this value in for all of the x's. So let's go ahead and plug in the -1. And we get -3 over +1, which is -3. If on question 2 we attempted to do the same thing, if we plugged in a -2 right there, we'd have -2 plus 2, it's 0. It's not going to work. So oftentimes what that means is there's some simplifying that needs to be done with that expression. So in the numerator, if you factor out an x, then the x plus 2 factor in the numerator and denominator cancel out. So the problem is limit as x approaches -2 of x, and now we can plug -2 in just for the x there. And what we get is -2. Okay, question 3 specifically does say to use the limit definition of the derivative to find the derivative of this function here, but also once you have the derivative, use that to find the slope of the tangent line at that point. So limit as delta x approaches 0 . Remember, we had a delta x in the denominator. Numerator was f of x plus delta x minus f of x. So we need to figure out what is f of x plus delta x first of all. What I've always recommended when doing a problem like this, when we're inputting something like this into a function, is rewrite the function, but instead of x's, make it an empty set of parentheses. So 3 parentheses squared minus 2. Inside the parenthesis, we're going to place the x plus delta x, and then simplify. X plus delta x squared is just x plus delta x multiplied by another x plus delta x. And then multiplying those two terms together here, we're going to get x squared plus 2x delta x plus delta x squared. Then distributing the 3, so that is f of x plus delta x. This is the expression that's going to replace right there. And then f of x, we already know that f of x is equal to that. So come over here, Got the delta x there in the denominator. F of x plus delta x, this expression right here, just going to replace with that expression there. So we've got 3x squared plus 6x delta x plus 3 times delta x squared minus 2. So that's f of x plus delta x. Now we've got to subtract the original function, and that's got to be done in a parenthesis. 3x squared minus 2. Now at this point, if you recall, at this point of the problem, a lot of things are going to cancel. Any term that doesn't have a delta x should cancel. So this 3x squared and that negative 3x squared are going to cancel. Remember here we got minus and negatives, so that's going to turn into a positive. So that positive 2 can cancel with that negative 2. So in the numerator, what we have left would be a 6x delta x plus 3 delta x squared all over delta x. In the numerator there, we can factor out a delta x, leaving us 6x plus 3 delta x over delta x. Now that we've got a delta x factored out, we can cancel it with the delta x factor in the denominator. So we end up finding the limit as delta x approaches 0, and we don't have a fraction anymore. We're just finding it of 6x plus 3 delta x. Now delta x here is going to take a value of 0, which means that that term just becomes 0. So the limit as delta x approaches 0 is equal to 6x. This is the derivative. And remember, you can use the derivative to find the slope of the tangent line at a particular point. So slope of the tangent line at the point 2, 10, we're going to use our derivative and then plug in the x value of the point, which is 2. So the slope of the line tangent to the function at the point 2, 10 is 12. Part, let's see, I wonder if that's supposed to say question 4. Is that a typo? Let me look over here. Nope, there's a B and a part C for question 3. So 3A was using the limit definition to find a derivative. Part B and part C were using other rules of differentiation, particularly the power rule. But what needs to happen first is a quick rewrite. So you don't want to take a derivative if you have an expression or a function in radical notation. You always want to make sure you have rational exponents. So taking the derivative now of this with respect to x is a dy dx. Now we're going to use the power rule. Remember, coefficient and exponent are going to multiply. So 2 times 2/3 is 4/3, and we subtract 1 from the exponent. Again, I'm perfectly okay if you leave your answer in this form. However, if you want to be matching up with your answers in the back of the book, for example, negative exponents would go in the denominator. So the answer would look like that. To part C, we're going to move this term to the numerator, give it a negative exponent. It's going to make it easier to differentiate, because now we can just use power rule. So finding the derivative with respect to x. Simple power rule says the coefficient there is going to multiply with the exponent. So that's negative 15 times y, then subtract 1 from the exponent, gets negative 6. Y, what am I talking about? X. Let's try that again. X to negative 6. Okay. And again, if you wanted to be the most precise, you would move that expression down to the denominator to give it a positive exponent. Okay, question 4 is from section 2.3. These were some of the applications of the derivative. In this case, we're looking at velocity, average velocity, and actually I think there at the bottom, part E, acceleration, that actually came from section 2.6. So two things to really pay attention to here. Average velocity and instantaneous velocity, remember, were two different things. Average velocity is simply the slope of a secant line from the position function. Instantaneous velocity comes from the slope of the tangent line. Tangent line is the first derivative. So average velocity is going to come from the position function s of t. So negative 16t squared, that's the effect of gravity. And then you add the initial velocity, 64 feet per second. And lastly, you add the initial height. But it says here the ball was thrown from ground level, so the initial height is 0. And don't really need to add 0 to the end of that. So there's the position function. So average velocity is the slope of the secant line of the position function through 2 points. These are both x values right here, or values of time. So what we need to do is find the position at 2 seconds, subtract the position at 1 second, or sorry, 0 seconds, that's the first x value, and then 2 minus 0. This is just the slope function. Here in the numerator we have the difference in y, and here in the denominator we have the difference of x. Change in y divided by change in x. That's the slope of a line. So s of 2, negative 16 times 2 squared, 64 times 2, s of 0 is just going to be 0. We plug in a 0 for all of those t's. So 2 squared is 4, 4 times negative 16, negative 64, and then 64 times 2, 128, that equals 64. So we're going to have 64 minus 0 over 2, which is 32 feet per second. That's the average velocity of the ball for the first 2 seconds that it's thrown. Instantaneous velocity comes from the derivative of position, so the derivative of position is equal to velocity, so in this case it's going to be negative 32t plus 64. I'm just taking the derivative there of that position function. So now we just need the velocity at 2 seconds. So the velocity is 0 feet per second. I think we've seen this before. We've talked about this before. You think, how can the ball not be moving? Well, at 2 seconds, what's happening here is the ball has reached its highest point, so it stopped moving upward, and in that exact moment, it's moving from upward to downward. So when it's reaching its maximum height there, the velocity changes to 0 for that moment in time before it starts to move back down. Now, how long will it take for the ball to hit the ground? For the ball to hit the ground, we're talking about a position. We're not talking about how fast is it going to be traveling or the acceleration. We're talking about how long is it going to take for the ball to hit the ground. That's a position, and the position of the ball when it hits the ground is 0. So we're trying to solve the equation S of t equals 0. So we're trying to solve that equation right there. So we can pull out or factor out a negative 16t from the equation. That's going to leave us with t minus 4. So we have two different values of t that's going to make this equation 0. T equals 0 and t equals 4. These are time values, so these are seconds. So obviously t equals 0, 0 seconds, the ball's on the ground because that's where it started at time equals 0. We're going to use this answer. After 4 seconds, the ball is back on the ground. So at time equals 0, the ball started on the ground. It took 2 seconds for the ball to reach its maximum height. So because a parabola is symmetric, it's going to take 2 seconds for the ball to fall back down. That gives us our 4 seconds from the ball, for the ball to go from ground level up to its maximum height back down to ground level. So at that moment of time here with 4 seconds, how fast is the ball traveling? So at the moment the ball hits the ground, what's the velocity? This is implying instantaneous velocity, so we need the velocity function, which we looked at earlier on part B. So the velocity at 4 seconds then, because it took 4 seconds for the ball to hit the ground, (32 times 4 is 128, so that's negative 128 plus 64. So the ball is traveling, or the velocity of the ball is negative 64 feet per second. It's negative because the ball is traveling towards the ground. The acceleration is the derivative of the velocity. Acceleration is a force, and the only force acting on this ball is gravity, and negative 32 feet per second squared is the effect of gravity on any falling object. Okay, so question 5 was another application of derivative. This was called marginal. This is still from section 2.3. I'm actually going to do part B. Well, yeah, I guess we do it just in order. Do part A and then part B. Marginal revenue is the rate of change of revenue. That's what marginal is. Marginal is a rate of change. Rate of change is a derivative. So for part B, we're going to be finding a derivative. One helpful thing about marginal revenue or marginal profit or marginal cost is we can use that to approximate the actual change in revenue or the actual change in profit for a 1 unit or a certain number of unit increase. So for part A, we're going to find the actual change in revenue for a 1 unit increase if we increase production from 8 units to 9 units. So that's an actual increase, which is going to change revenue of 1 unit. Marginal revenue is going to tell us the rate of change of revenue as far as dollars per unit. Dollars per unit implies a 1 unit increase starting at x equals 8. So a 1 unit increase would be from 8 to 9. So that's going to help us approximate the answer from part A. So for part A, we just need to find the revenue at 8 units and compare that to the revenue at 9 units and find the difference. So the revenue at 8 units, just going to plug 8 into the revenue function. The revenue at 9 units, same thing, just plug in a 9 into the function. So 150 times 8, and then 150 times 9 And then, well, let me get my calculator for this one. Okay. So I've got these on here. This is in terms of dollars. So the revenue for 8 units was $1,152. The revenue increased to $1,289.25 when they sold 9 units. So there was an increase of revenue. The question is, what's the additional revenue? So how much was increased? So we're just going to do revenue for 9 minus the revenue from 8. So that's this value. Subtract this value. We're going to get $137.25. So the the revenue increased when production changed from 8 units to 9 units. The revenue increased by $137.25. So this change in revenue can be approximated by a marginal revenue. A marginal revenue, again, is a rate of change because it's a first derivative. The rate of change is in terms of dollars per unit, per 1 unit. And since we're talking about a 1 unit increase here, the marginal revenue at 8 units should be a very close approximation to the actual change in revenue. So marginal revenue is R prime. So we're just going to find the derivative of this function. So 150x, the derivative is 150. 3/4 x squared, the derivative of that is going to be, we're going to have to take this coefficient, multiply there. So 3/4 times 2 is 6/4 times x, and we decrease the exponent to x to the first power. And then we can simplify the fraction. So now the marginal revenue when x equals 8, we can just plug in an 8. So this is 150. 3/2 of 8 is 12. 150 minus 12 is $138 per unit. So we've kind of talked about part C. Interpret the results for parts A and B. Why are they so similar? So for part B, the marginal revenue approximates change in revenue for a 1 unit increase at x equals 8 units. The marginal revenue can approximate the change in revenue for a 1 unit increase at 8 units. And the reason I say 1 unit increase is because the marginal revenue is number of dollars per unit. Per unit implies per 1 unit, so we need a 1 unit change there. So for part A, it was a 1 unit change from 8 units to 9 units, making marginal revenue for that a pretty good approximation. Okay, question 6. We're going now into section 2.4, where we learn some additional rules of differentiation, product rule, quotient rule. So it doesn't explicitly state which rule to use. That's for us to decide based on whether the expression's in the form of a product or the form of a quotient. So for question 6, we've got this binomial multiplied by that binomial. So those are forming a product. So we're going to use the product rule. If we want to give function names to each of these expressions, f, for example, and g, then y is equal to f times g. the product rule of differentiation says that the derivative of a product is f prime times g plus g prime times f So f prime would be the derivative of this factor of that product. So the derivative of, excuse me, the derivative of that would be negative 9x squared. And then that's multiplied by g. And that's added to g prime. So now g prime would be the derivative of that factor of the expression. That would be positive 9x squared multiplied by f. And then we simplify to either factors that are all multiplying each other or individual terms added together like a long polynomial. So I'm just going to go ahead and distribute some terms here. So negative 9x squared times 3x cubed, that's negative 27x to the fifth minus 45x squared, and then if we distribute there in the next part, that's negative 27x to the fifth plus 27x squared. Combining some like terms, we're going to have negative 54x to the fifth. And then, let's see, the 45 has an x squared term and the 27 has an x squared term. So those can combine. Let me make sure I get my math correct here. That's going to be 18. So negative 18 x squared. Now that's one option for question 6. The other option, I did mention at times, not always, but at times there's a way around using the product rule. You could just multiply this expression together before taking the derivative. So if we did that, we would get negative 9x to the sixth, and then we'd have a negative 15x cubed and a 9x cubed. Negative 15 and 9 would give us negative 6x cubed, and then we'd have a plus 15. So this is the expanded form of that expression. And then you could take a derivative of individual terms. The derivative of that first term is negative 54x to the fifth. The derivative of the second term is negative 18x squared, and the derivative of 15 is 0. So you can compare, get the same answer there. Question 7. This function's in the form of a quotient. So we can name the numerator f, for example, and the denominator g. And the quotient rule is g times f prime minus f times g prime all over g squared. So we can start with g, which is 4x to the fourth, times f prime, which is going to be 8x, minus f times g prime, which is 16x cubed all over g squared. Alright, this is
really just distributing some terms in the numerator and then combining like terms. So here the 8x into that one is going to be 32x to the 5th plus 32x, and then distributing the 16x cubed in there. 16 times 4 is 64, so this is minus 64x to the 5th, and then we're going to have a plus because we have a negative here and a negative here. Negative times a negative is positive, so plus 16x to the 3rd and then looking up in the numerator, we have x to the 5th terms that are alike, the 32 and the negative 64. So if you combine those, you get negative 32 x to the 5th plus 16x cubed plus 32x all over 4x to the 4th plus 4 squared. So that's our example of the quotient rule.
Next question, question 8, is an illustration of the chain rule because we have an inside function and an outside function. So if you recall, the chain rule states we need to deal with the outside function first. The outside function has a 1 coefficient, so it's really just the power rule. The coefficient multiplies with the exponent there. So 1 times 3 is 3. Remember, nothing happens at this point to the inside function. The outside function exponent decreases by 1. But now we multiply this by the derivative of the inside function, which is negative 2x. The negative 2x can multiply there with the 3, making negative 6x. Question 9, before taking any derivative, you need to rewrite the equation to have a rational exponent. And now, it's much like question 8, where it's an application of the chain rule still, but mainly power rule. So we have coefficient there, which is going to multiply with that exponent. So 1 times 1/3 is 1/3. At this point, nothing goes on with the inside part. You decrease the exponent by 1, so that's going to be 1/3 minus 1 is negative 2/3, and then we multiply this by the derivative of the inside function. The derivative of 4x squared minus 3 is 8x. And then the 8x and the 1/3 can multiply to 8x over 3. And I'm perfectly happy if you leave the answer in this form, but like at the beginning of this pretest, technically speaking, negative exponents are supposed to become positive exponents. So you would write this, the 8x would stay in the numerator, 3 stays in the denominator, and then the 4x squared minus 3 would also move it to the denominator and would have a positive exponent. Now, as is often the case with product rule, especially product rule is often combined with another rule, in this case the chain rule. We have this factor multiplied by this factor. So this is going to be a product rule where we can call this one f and this one g, but then particularly with g represents a factor that can be used with the chain rule because there's an inside function and an outside function. So there's a lot going on with this problem. So I'm going to call this one f times g. So then according to the product rule, we have f prime times g plus g prime times f. So following that pattern, f prime is negative 8x. I'm going to multiply that by g. And then you add that to g prime. This is where the chain rule is going to come in. So if we're just looking at g, then it has a coefficient of 1 in front of it right here. So the 1 and a 2 have to multiply. Nothing happens to the inside part. And then you decrease the exponent, so it just becomes a 1. And that's supposed to be a 4. We don't really need a 1 exponent. So then, going back to the chain rule, this is still g prime. We need to do the derivative of the inside part, so that's going to be 8x cubed. Now this right here, this is just the g prime part of this product rule. We still need to multiply this whole thing by the f function, which is negative 4x squared minus 5. Now, I'm going to try to factor some things out. Well, first simplify and then factor out some common factors. There's not much to factor out there or to simplify. But here, the 2 and the 8x cubed, I'm going to call that 16x cubed. And then we have the 2x to the 4th plus 1, and then that's multiplied by negative 4x squared minus 5. So this plus sign, I'm going to consider separating this problem into a left side and into a right side. So if I look at the left side, I need to compare what it has in common with the right side. They both have a 2x to the 4th plus 1 factor. And they both have at least an 8x I can factor out. So those are going to be my common factors that I'm going to factor out. Matter of fact, I'm also going to factor out the minus sign with it. So I'm going to factor out a negative 8x and a 2x to the 4th plus 1. So this is the factor that I'm factoring out of both this side of the equation and that side of the equation. So first looking at the left side, if I factor this out of that, I'm taking everything out or factoring everything out except for the 2x to the 4th plus 1. There were 2 of them, and I factored out 1 of them. Now, because I factored out a minus sign from that plus sign, it's got to change into a minus. So, fix that there. So it's going to be minus. Now I took out a negative 8x from 16x cubed, so that's going to leave negative 2x squared. I factored out the 2x to the 4th plus 1, but that leaves the negative 4x squared minus 5. So this little guy here, the big parenthesis, I've got a 2x to the 4th plus 1, and then if I multiply those two together, so let me write this down, 2x to the 4th plus 1, and then I'm going to have a plus 8x to the 4th, and then a plus 10x squared. So that's going to be 10x to the 4th plus 10x squared plus 1. So that's this right here would replace all of that, all of this right here. So the final version of this answer is the negative 8x plus 2x to the 4th plus 1, and then we've got this expression there, the 10x to the 4th plus 10x squared plus 1. All right, question 11, we're just finding the third derivative. So we got to go in order, find the first derivative, then the second derivative, and finally the third derivative. The first derivative, all of these derivatives are just power rules. So this is going to be 8x cubed minus 9x squared. The derivative of that would be the second derivative, 24x squared plus 18x. The derivative of that would be 48x plus 18. Question 12, this is from section 2.7, implicit differentiation. Implicit differentiation, remember, is really just an application of the chain rule. Because, for example, y represents a function of x. It's implied that y is a function of x, so that x is an inside function. So y is an inside function, and then we have that outside function there, which is why it's a chain rule. What makes this problem a little bit, I guess, more challenging, more fun maybe, is the 3x and the y cubed are multiplying each other. So that's a product rule. And then same here, the 2x squared and the y are multiplying each other. So there's another product rule there. We're just going to be real careful to recognize that. Y cubed and 3x squared have to be, you got to be careful with that because it's a product rule. And the same thing there, the 2x squared and the y product rule. I'm just going to do this one term at a time. The derivative of 5x with respect to x is 5. Now I'm to this term, and if I think about separating this term into an f times g, then I can use the product property, which says f prime times g plus g prime. Now g prime is going to be the derivative of y cubed. That's going to be 3y squared. And then that's the derivative of the outside function. Now we need the derivative of the inside function, which is the derivative of y, which is dy dx. So again, we've got, this is f prime times g plus g prime. This whole thing right here is, that whole thing is g prime, so we just need to multiply by f to complete the product rule. So multiply that by f, which is 3x. Now moving on to the next term, again, this is 2x squared times y. So this could be another product rule where we have another f and a g. So if we're going to do the product rule, it says f prime times g plus g prime. The derivative of y is dy dx times f. Now we move on to the derivative of that expression, or the derivative of after the equal sign. The derivative of 3 is 0. So I'm going to multiply those two together. The 3y squared and the 3x is going to give me 9xy squared dy dx. And then this here, well, it's really just that. It's 4xy. And then 2x squared dy dx. And then I've got the 5 plus 3y cubed. That equals 0. So the point here is to get dy dx by itself, because I want to end up eventually with dy dx equals something. But what that means is I need a single dy dx. Right now I've got a couple of them over here. So what has to happen now is any term that has a dy dx is going to stay on the left side of the equation. Any term that does not, like this 4xy, that doesn't have a dy dx, the 3y cubed and the 5 none of these have dy dx's, so I'm going to move those to the other side of the equation by subtracting. So the 9xy squared dy dx stays on the left. The 2x squared dy dx also stays, but I subtracted the 5 over, I subtracted the 3y cubed over, and I subtracted the 4xy over. Now both of these terms have a dy dx, which means it's a common factor. So if you factor it out, you're left with 9xy squared plus 2x squared and then we can get dy dx alone by dividing, because now dy dx is multiplying. So if you divide on both sides, cancels it there, leaving us our single dy dx, or y prime, okay. Last page, section 2.8, related rates. Now it's specifically telling us that this is related rates. It may or may not on the exam. It may just be solve this problem. You've got to be able to read through the problem and know that it's talking or asking you to solve a related rates. Related rates really is nothing more than implicit differentiation, where you're taking the derivative of one variable with respect to another, where two rates are related. For example, we have a radius that's increasing at 4 meters per minute, and it's asking for the area. How fast is the area increasing? So that's a rate because it's increasing. How fast is a rate. And since the area is related to the radius of a circle, these rates are related, hence related rates. So how fast is the area of the spill increasing? The area spreads in a circle, so the area of a circle is pi times r squared. And it wants how fast is the radius, or how fast is the area increasing with respect to time in meters per minute. This is the rate we're going to be comparing, meters per minute. Minute is a measurement of time, so when we differentiate, we know that we're differentiating with respect to time because this is per minute. That's really important. I've seen this problem very often get confused, and students try to differentiate with respect to r because they see an r right here, but the rate they want us in is per minute, so we have to be differentiating with respect to time, and this should be something that you start to recognize. This variable and that variable aren't the same. That's why this makes this implicit differentiation. So this implies the radius is a function of time, which it is because it's increasing at a rate compared to time. So the derivative of a with respect to time is dA dt. That's going to give us the rate of change in area in terms of minutes. Now the derivative of pi r squared is 2 pi r, but that's just the derivative of the outside part. The derivative now of the inside part, r, is dr dt, and perhaps should have started with this. Actually, a good way to start any application problem is state what we know. We know that the radius increases at a rate of 4 meters per minute. So since it's a rate, it's not r equals 4, it's dr dt equals 4 meters per minute. So that's going to replace our dr dt, and it says find the rate of change of area when the radius is 15 meters. So now we know what to plug in for r. So So when the radius is 15, this is going to be 2 times pi times 15 times 4. 15 times 4 is 60. 60 times 2 is 120. So this is 120 pi meters per minute. It's actually meters squared per minute because it's an area. Okay. Question 14 is going to turn out to be a related rates because it says that sales, which is x, so x is increasing 15 units per day. So dx, and per day, day is a measurement of time, so it's dx over dt equals 15 units per day. Find the rate of change in profit. So what we're supposed to find is the rate of change of profit. Rate of change, remember, is a derivative, so dp, and it's dp over, and now we've got our side as a dp over dx, dp over what? And the rate that they want us in is right here, per day, so that's a measurement of time. So they want us to find dp dt. So profit is given already. dp dt is just the derivative. With respect to time, though, so you got to be really careful. Oftentimes students look at 300x and think, well, the derivative is just 300. But remember, we're differentiating implicitly here because t and x aren't the same variable. So the derivative of 300x is 300, but then we have to multiply by the derivative of x with respect to time, which is dx dt. Now we move on to the next term here. The derivative of 1/2 x squared is the 1/2 times the 2 becomes 1, and 1 times x is x. And then you decrease the exponent to x to the first power. But again, this is implicit differentiation. This was just the derivative of the outside function. Now we need to multiply by the derivative of the inside function, x, and the derivative of x with respect to time is dx dt. So dx dt we know is 15 right there, and then to plug in for x, it says when 150 units have been sold. So find dp dt when x equals 150 is what we're supposed to find. So dp dt is 300, dx dt is 15, minus x, which is 150 times 15.
Okay, excuse me, 300 times 15 is 4,500. 150 times 15 is 2,250. Subtracting those two is $2,250 per day, because remember, this is a rate. dp over dt is the change in profit over dt, which is time. So it's increasing at a rate of $2,250 per day when production is, or when sales is 150 units, and it's increasing at 15 units per day.